Oh good, you're back. So you've been looking at several important building blocks like the idea of a linear discriminant and soft labels using the logistic function. So in this lesson, I want you to put these building blocks together, specifically by applying maximum likelihood estimation to the logistic classifier model. All right, so let's get started. As a quick reminder, we're trying to fit a model to a set of labeled data, and the model has two components. The first is a score that assigns a value to every point in space. We happen to pick a linear function, which is often a good place to start. Now, the specific choice of theta determines a separating boundary or discriminant between positive and negative values. So to get labels for classification, you put that score through the logistic function. The net effect is to assign values between 0 and 1, depending on the distance of a point from the boundary. Now, the motivation for a soft assignment is that real-world data is not cleanly separable. So, how do you calculate theta? Remember the maximum likelihood idea. Assume you can write down a function that measures how probable or likely the data are for a given theta. Now, one such function is the log likelihood. Let's further assume that observations are themselves independent. Then, the log likelihood can be written as the sum of the log likelihoods for each observation k. And remember, this little lk function is just the likelihood of an observation. So that's the conditional probability of the observed label, yk, given its coordinates x hat k and theta. So let's determine this function now. Start with the logistic function with a linear boundary, g of theta transpose x hat k. Recall that it maps the real number line to the bounded interval 0, 1. Therefore, it's a function that we can try to interpret as a probability. Let's call this little gk for short. Now consider two cases. First, suppose the observed label equals 1. Then we can define the probability of seeing this label for a given model as little gk. Now what if instead the observed label is 0? Well, then its probability under this model must be 1 minus little gk. Now there's a little trick to combining these cases into a single formula. The result is gk to the power yk times 1 minus gk to the power 1 minus yk. So we're using the fact that yk is either a 0 or a 1 to implement a kind of mathematical if statement. Now the first term corresponds to the observed label being 1. If the label is instead 0, then this term is just 1, and so it's effectively ignored. The second term is for a label of 0, and it's ignored if the label is instead 1. Now this form is especially convenient to the task at hand. So why is that? Well, taking logs of this function is easy. It's just yk times log gk plus 1 minus yk times log 1 minus gk. Okay, now here's a second reason for this form. To find the maximum, you eventually need to compute the gradient of the log likelihood. So as an exercise, you should try to calculate it on your own. Let's close with one final observation. There are some nice linear algebraic formulas for the log likelihood over all observations. So let y, x, and theta be our usual objects, the vector of responses, the data matrix of coordinates, and the vector of parameters. Let's also define u to be the vector of all ones. Using all the mathematical tools at your disposal, you can show the following. First, here's one way to write the log likelihood. Y transpose times log of g of x times theta plus u minus y transpose times log of u minus g of x times theta. Now here's a slightly more compact version. Y transpose x theta plus u transpose log of g of minus x theta. Both formulas use the fact that the sum of the elements of a vector z is equal to u transpose times z. So that's a handy factoid for converting between scalar and vector formulas. So to sum up, this lesson is about applying the mathematical framework of maximum likelihood estimation to the classification problem. But MLE is actually a generic tool, and you can apply it in a bunch of other settings. So for example, you can derive linear regression using MLE, and you might have seen that in a separate course on regression. The key step is really coming up with a model of the likelihood in this problem. Now, there's a computational reason to go through these steps as well. So you remember you ended the lesson with the linear algebra formulas for calculating the log likelihood. And so that will lead directly to a compact and efficient implementation. So there's a notebook to go along with this lesson, and it'll walk you through that process. So why don't you go ahead and do those now, and I'll see you when you get back.